Hello everyone. So this is week 7 and we are going to continue with the network layer, which is chapter 4, and in this lecture we are going to talk about routing algorithms. I'm going to only talk about only one algorithm, which is the Dijkstra's algorithm. So let's start with this. Okay, so my topic today will be covering the routing algorithm, and under routing algorithm I'm going to cover only the link state. Rest all we will cover after the midterm. Alright, so let's start with it. Routing, interplay between routing and forwarding. We understood the difference between routing and forwarding in the previous chapters. So, routing algorithm, the purpose of the routing algorithm is to find out the end-to-end path between the source and the destination. So, routing algorithm mainly helps to determine or to establish the path between the source and the destination through the network, whereas forwarding table determines the local forwarding at this router. So, forwarding means if the packet arrives at a router, then the router will examine the IP address in the packet's header. Then based on that address or based on that data, it will consult its forwarding table, and then it will direct this packet to the appropriate output link. This is called as forwarding table. And routing means determining the complete path from source to the destination. So in this lecture we are going to talk about routing algorithm. Alright, so basically network is considered as a graph. So we use the graph to represent a network. So graph, as we know, that it consists of nodes and edges. So if we visualize a network as a graph, then what are nodes and what are edges? So nodes are the set of routers. For example, in this picture, if you can see U, V, W, X, Y, Z, these are all routers. And edges are the set of the lines or the interconnections between the routers. So for example, the edge set of links between UV, UW, UX, VX, XW, YW, and YZ, WZ, UW. So all these are the set of links. Graph abstraction is useful in other network context also. For example, in the point-to-point networks, where we have n number of peers and e number of TCP connections. So basically, when we are going to determine the routing, we are going to visualize the network as a graph. Alright, now before we start with the algorithm, let's understand a few things related to the graph terminology and network terminology. So to determine the cost between X and Y, CXY means cost of a link between X and Y. So for example, the cost of a link between W and Z, CWZ. This means that cost of a link between W and Z, which is 5. So if I write C, U and V, U comma V. So this means that cost of the link between U and V, which is equals to 2. Now cost could always be length or inversely related to the bandwidth, or it can be related to the congestion. So cost of a path from link X for all the links, for the links X1, X2, X3 up to XP is the cost from X1 to X2, X2 to X3, X3 to X4, and XP minus 1 to XP. Now, the question arises, what is the least cost between U and Z? How to find out? Because if you see, this router is at one end and the Z router is at another end. So what is the least cost between these two routers? Because we can easily determine, because we can visualize this and it's a small graph. But imagine when in case of the internet, the network of networks, when we are sending our data from like for example Saudi Arabia to the other corner of the planet. So what is the least cost? So what is the least cost between U and Z and how to determine? So routing algorithm will find the least cost path. So what is the purpose of the routing algorithm? It will find the least cost path between the two routers or the two links. Alright, now classification of the routing algorithms. Routing algorithms can be divided into two categories. We can have global routing algorithm or decentralized information. So what is a global routing? In this, all routers have complete information about the network topology and the link cost. So a global routing algorithm will compute the least cost path between a source and the destination using the complete global knowledge about the network. That means this algorithm will take the connectivity between all the nodes, all the link cost as inputs, then it will do the computation. So this then requires the algorithm to obtain this information before actually performing this calculation. And the calculation can be performed on one site, it can be a centralized, or it can be replicated on the multiple sites. But the main feature over here is that global algorithm has a complete information about the connectivity and the link cost. So in practice, the algorithm with the global state information is normally referred to as the link state algorithm. We will study link state algorithm. Decentralized. In this lecture we are going to cover link state algorithm. Decentralized. So decentralized is a router knows physically connected neighbors and the link cost of the neighbor. So for example, if I am a router, I will only know the link cost and my next connected routers. So it's an iterative process of computation and exchange of information with the neighbors, and the example is the distance vector. So in case of decentralized, the calculation of the least cost path is carried out in iterative and distributed manner. No node has a complete information about the cost of all the network links, and instead each node begins with only the knowledge of cost of its directly attached link. Then through each successive iteration by the process of calculation and exchange of information, subsequently the router comes to know and calculates the least cost path to the destination or the set of destinations. So this is the difference between the global and the decentralized algorithms. Example of the global algorithm is link state and example of decentralized is distance vector. Alright, next is static or dynamic. So static or dynamic, another way to classify the routing algorithms. In static routing, routes change very slowly over the period of time and often as a result of human intervention. So often as a result of manual modification of the routing table. Whereas dynamic, as the name suggests, dynamic routing algorithms, they change the routing path as the network traffic loads or the topology changes. So there are the routes change more quickly, periodic updates are there. A dynamic algorithm can either run periodically or in direct response to the topology when there is a link change or when there is a breakage in the link, so then it will run. So it is more responsive to the network changes and it is more susceptible to the problems such as routing loops or oscillations in the routers. So, and this is another way of classifying the routing algorithms. Alright, so in this lecture I am going to talk about only the link state algorithm. Okay, so let's start about what is a link state link state algorithm. Now link state algorithm, first of all remember it belongs to a class of the global routing algorithm. So the network topology and the link cost are known to all the nodes. How it is known? It is accomplished, this calculation of the network topology and link cost calculation is accomplished via link state broadcast. all nodes, they have the same information, they have the same calculations. So Dijkstra's algorithm, we will use the Dijkstra's algorithm to find the least cost. The link state routing algorithm, now we will discuss, is the Dijkstra's algorithm. Now what this algorithm does, it computes the least cost path from one node to all other nodes. So from example X to all the other nodes which are attached in that topology. Then it gives the forwarding table for that node, and it's an iterative algorithm. After k iterations, known as least cost path to k destination. So after k iterations, least cost path to k destinations will be calculated and will be known by the source node. Alright, this is not an example of the Dijkstra's algorithm. Rather, for example, if we want to calculate the shortest distance from A to C, how are we going to calculate? It's not an example using the Dijkstra's. So what are we going to do over here? For example, if we want to calculate from A to C, so first of all we will calculate from A to A the cost. We will not calculate the cost from node to node. A to A will always be 0. Okay, so here what we have done, we will tick the nodes which we have visited, and then we will update also. So from A to A the cost is 0. Now A is attached to B, so from A to B the cost is 6. But at the same time we will check that is there any some least cost to reach to that link. So I have the least cost. For example, the least cost is from A to D, then from D to B the cost is 3. So I update, and in the third column I will update the node or the path how to reach B. So I can reach B via D. Now from A to C, if we calculate, I have many paths. For example, I can reach from here from A to D, D to B, then from B to C. The cost is 2 plus 1 3, 5 plus 3 8. 5 plus 3 5 plus 3 8. Then I have from A to D, D to E, E to B, and E to B and B to C. So 3 and 5 plus 3 8. I think it should be 8 over here, not 7 over here. Or if I go from here from A to C directly, it is 6 plus 5 is 11. It's too much. It's very high cost. So the least cost is to reach from E over here. The cost to reach D from A is 1. There is no, there are other ways, but they are costly, and it is from the link A. Cost to reach from link A to E is it's 2. It's 2 from A to D and from D to E. So A to D and D to E, it's 2, and it is via D. So this is how we can visualize this graph. Now, what is Dijkstra's algorithm? What is the algorithm, and how we are going to calculate the least cost by using the Dijkstra's algorithm? So in Dijkstra's algorithm, as we discussed, net topology and link cost are known to all nodes, which is accomplished via link state broadcast. All nodes have the same information. It computes the least cost path from one node, that means from the source node to all other nodes, and then it gives the forwarding table for that node. After k steps or after k iterations, least cost path to the k destinations are calculated. Alright, now let's discuss some of the notations before we go further. CXY is the cost of the link from X to Y. So we call it as link cost from node X to node Y. It is infinity if the X and Y, they are not direct neighbors. If they are direct neighbors, they will have some number. DV, so distance from source to destination. So it's a current value of cost of path from source to destination B. PV is the path, or we call it as predecessor node along the path. So what is the previous node along that path to reach from the source to the destination or to node V. And N dash, it is the set of all the nodes whose least cost path is known definitely. So these are some of the notations which we will be using. Alright, so let's talk about, since this is a global routing algorithm, it consists of an initialization step which is followed by a loop, and the number of times the loop is executed is always equal to the number of nodes in the network. So please remember, the number of iterations that we will be performing in this will always be equal to the number of nodes in the is equal to the number of nodes in the network. And when this algorithm will terminate, the algorithm will have calculated the shortest path from the source node to the every other node in the network. Alright, so let's just check about it. In the beginning, it's the initialization phase. So in the initialization phase, what does n dash have? It has set of all the nodes. For all the nodes v, if v is adjacent to u, so if v and u are direct neighbors, then we will calculate the distance from u to v by calculating the cost of link from u to v. Otherwise, what will happen? It will be infinity if they are not direct neighbors. Now then there will be a loop. So we will find w in n naught such that dw is minimum. So we will add that node w or the intermediate neighbor to the set of nodes. Then we will update the distance from source to the destinations. How we will update? We will calculate the minimum of distance v and distance w plus cost from w to v. So distance from v to w and cost from w to v. So if the new cost is lesser than the old cost to v, then we will update it. Otherwise, we will keep it as old one. So we will do this loop will be carried out until all the nodes in n dash have been visited. So let's just talk about this algorithm. Okay. So if you see, this is the way how you are going to solve these questions. Step n, which will consist all the nodes. We will start from the source to the destination. For example, in this we want to find out the cost from minimum cost from u to z, for example. So in this case, when we want to find out, it will find actually the minimum cost path from v to all other nodes also. So first of all, we will add over here all the nodes and their path. For example, distance of v and path of v, w, path of w, dx, px, dy, py, dz, pz, right? So this is how we will start with the notations. We will start from 0. First of all, we will visit the node u. In this, first of all, we will visit the node u. Now we will check cost from node u to v is what? 2. And what is the predecessor or what is the path? It is u. So we put u here. Cost from u to w. So it is 5. Even if we go like this from u to v to w, it's again 5. So what is the predecessor node? Predecessor node is again u. From d to x, from u to x, cost is 1. And what is the predecessor node? It's u. Now, since u is not directly attached to y and u is not directly attached to z, so what we will put? We will put infinity over here. Going to the algorithm, if they are not adjacent neighbors, we will put as infinity. Now in the next step, what we are going to check, out of these, the nodes which has a least cost, we will traverse that node. So out of these, the least cost is for the x node. We will add x to our set of nodes which we have traversed. So this n dash will basically consist of all the nodes which we have traversed during the particular time, and we will increment the iteration by 1. Now from x to u, the cost is the same. We are not going to update it. Now from x to w, alright, x to w, the cost is 3, and from u to x, the cost is 1. Now we go over here. We need to check, update the distance for all v adjacent to w which are not in n dash. Now we have to find out the minimum cost path, right? So the minimum cost path is, it was 5, right? Now if we calculate from x to w, from u to x we know it's 1. Now plus cost from w to v, right, which is over here, dv. What will I write? Cost from d to x I already know, plus cost of the link from w to v, right? Dx, what is dx? Distance to x we have already calculated, which is 1, plus cost from w to v, cost from x to w, cost from x to w is 3, which is 4. So 4 is less than 5. What we are going to do? We are going to update over here. So what we will do, we will put the cost as 4, and what is the predecessor node before w, which is x, we are going to update the node. Now from x to x the cost is always 0. From node to that particular node the cost will also be always be 0. Okay. Next is from x to y. X to y, previously it was infinity, but we can reach y. So how to calculate? Distance of x plus cost from x to y, right? Distance of x is 1, we already know it, plus cost from x to y is 1, which is 2 over here. And what is the predecessor node via which we reached y? It's x, we will put over here. Since we cannot reach z from x, we will put infinity here. Now it's not necessary that you fill all the columns, it's up to you, but whenever there is a change you need to update it, right? So it's not necessary. Okay, now out of these the least cost is either u or y. We can take anyone, this v or y, we can take anyone. So in this example they have taken y, you can also take v also. So now we add y to the list of nodes which we are traversing. So from y to u we need not to do, y to w, okay, we can calculate from y to w. Cost from u to y we already know, which is 2, and y to w is 1, which is 3, right? So u to y we already calculated 2, and y to w is 1, so it's 3. So we update over here, right? And what is the predecessor node via which we reached y? W, it is y, so we update the node over here. Next, from y to x, it's the same, we need not to do it. Okay, y to y is 0. Now we can reach from, y says that I can reach z. It is possible to reach z from y. So we will calculate the cost. From u to y we know it's 2, and from distance of y plus cost from y to z. Distance of y is, we have already calculated, which is 2, and cost from y to z is 2, so which is 4. So we put 4 over here, and the predecessor node is y. Now we need to still traverse v, w and z. So out of these the least cost is v, so we put v over here. V to v is 0, v to w is 3, but it's all we already have the least cost, so from v to w is 3 and u to v is 2, which is 5. Of course we will not update. Now v to x is 2 and u to v is 2, so 2 plus 2 is 4. We will not update because it's greater. V to y v to y, From V to W is 3 and W to Y is 4. We will not update because V is only attached to W, X and U. So we will not update over here. V is also not attached to V is also not attached to Z. So we will not update over here. So nothing is done over here. Now we are left with W, and you only need to write it if there is any successive update. If there is no update, you can leave it blank. That's perfectly fine. Okay, so now we are left with W and Z. Out of this, the least cost is for W. So we will add W to the list of traversed nodes. Now from W we can reach V, we can reach X, we can reach Y, we can reach Z. W to V is 3 and from U to W is 3. So we are not going to change it. W to W is 0. W to X, again it's 3 and 3 plus 3 is 6. We are not, because this we cannot get a lesser cost than 1. W to Y is 1 and the cost to reach to W is 3. 3 plus 1 is 4. So it's already 2. We are not going to change it. W to Z is 5, right? We need to change over here. Now W to Z is 5 and cost from D to W is 3 and W to Z is 5, which is 8, which is greater than this. So we are not going to change it over here. All right. So last one is Z. We already have explored Z and we already have the least cost of to Z, and there is no update in the last node. Okay. Just before I said that number of iterations should be equal to number of nodes in the network. Number of nodes are 1, 2, 3, 4, 5, 6. And how many iterations we have? 6 iterations. Alright, so what is the path from to reach from U to Z? This is, we have calculated the, we have done the calculations. Now what is the path? How to reach? So we need to reach to Z, that is our destination. Now I will go to the reverse order. From Z, I can reach Z from Y. This is the path. How I can reach Y? I will check Y over here. I can reach via X. How I can reach X? I can reach through U. So the least cost is 4 and the path is U, X, Y and Z. This is the path. Similarly, if you want to calculate what is the path, least cost path from U to Y, right? So the least cost is 2 and the path is, you want to reach Y. From Y, the node is X. How to reach X? X can be reached directly. So the minimum cost is 2 and the path is UXY. You need to mention the path also. Okay. For example, over here, what is the least cost path to reach from U to W? The least cost is 3 and the path is W, destination. How I can reach W? Y. Then how I can reach Y? I can reach from X. And how I can reach X? I can reach from U. So UXYW, which is UXYW, which is 3, U to X1, X to Y1, Y to W3. So this is the way how you can calculate the least cost path. Make sure you follow all these naming conventions while you are solving in the exam. Alright, now moving ahead. So the resulting is the shortest path tree from U, and resulting forwarding table in U will have V, if the destination is V, the link is U to V. If the destination is X, UX. If the destination is Y, UX. Now, if the destination is Y, it is UX. If the destination is W, again UX, right? and if the destination is Z, again the link is UX. So it's UX always. Now let's talk about the computational complexity of this algorithm. So what does it mean? That means given n nodes, how many computations must be done in the worst case to find the least cost path from source to or the destination. So in the first iteration, we need to search through all the n nodes to determine the node. W not in n dash, that has the minimum. So in the second iteration, we need to check n minus 1 nodes to determine. In the third, we need to traverse n minus 2 and so on. So the total number of needs we need to search through overall iterations is n into n plus 1 by 2, and the total number of comparisons are n square, because we need to do the comparisons at every step. So each iteration we need to check all the nodes. More efficient implementation is possible, and it may have the complexity n log n. A more sophisticated implementation can be with the help of the heap, and it may have the complexity as n log n. Link cost. Oscillations are possible. Oscillations means we are traversed between the loop. So link cost is amount of carried traffic. So there can be other implementations also which can give us a good or a better algorithm complexity, and the oscillations are possible. Okay. So this is the practice. You can practice this at your homes by using the Dijkstra's algorithm. You can find the shortest path, the least cost from 0 to node 4, from node 1 to node 5, from node 1 to node 4, and from node 4 to 8. So I think that is all about this lecture, and I'm going to finish this lecture over here. In the next lecture we will talk about the other routing algorithms. So thank you so much.